Welcome, I'm Rob Froney, and I'm here to talk about differential and common modes. First of all, let's look why this might be important. Just one example. Suppose we're in the university church. The preacher is up front speaking into the microphone, creating a very small voltage across the two terminals of the microphone. That microphone is connected through very long wires back to the back of the church where there are amplifiers. And these amplifiers are then connected to the speakers so everyone can listen. Those long wires act as antennas, and they pick up signals from the 60 hertz wiring in the church and any other electromagnetic interference. Fortunately for us, the two wires run parallel to one another, right next to one another, and they each pick up the exact same amount of interference. They act just the same as two identical antennas. And so when you look at the input of the amplifiers, you're going to have a signal. The difference between the plus and the minus is what you want to amplify, and then the average of those two relative to ground is what you don't want to amplify. Let's kind of look at how that works a little bit more. The symmetric signal, like you see here on the left, is identical on both sides. In other words, whatever one voltage does, the other voltage does the same. I'm kind of trying to represent voltages by heights. And the anti-symmetric thing has a zero average. You can see that in the middle. And whatever one signal does, the other one does exactly the opposite. So if one goes up, the other one goes down. Let's look at that a little bit more carefully here. But notice that the little wiggle going up and down may be smaller than the wiggle from the interference. So let's just look at a general signal. VI plus and VI minus. Those are the two voltages on the plus and minus wires. Here's the VI plus right here, and here's the VI minus right here, again representing voltages by heights. So we could also look at this in terms of the differential and the common mode, and that's really how I'd like to look at it. Let's see how they're related. You can see that the common mode voltage right here, that's the part both of them have in common, is the average. It's VI plus VI minus over 2. And then the difference signal is the difference between VI plus and VI minus. You can see that right here. And if I had the common mode and difference signal, it's equivalent to knowing the VI plus and the VI minus. Because if I want to find VI plus is the common mode signal right here plus 1/2 of the differential. And similarly for VI minus, it's the common part minus 1/2 of the differential. Let's look at how this works a little more mathematically here. Suppose we have a two-input, single-output system. This could be a two-input, single-output differential amplifier, but there are other devices that have a similar kind of topology. So if that's the case, the output voltage on the right can be written as a linear combination of the input voltages. And I would like to write it as a linear combination of the differential input voltage and the common mode input voltage. And we saw that knowing those two are equivalent to knowing the VI plus and the VI minus, as you can see even written in the equation on the right over here. Now, it's this way because this is a linear circuit, and so the output is a linear combination of the inputs. That's basically saying that superposition and proportionality apply. We can write this equation that we have up on top here, we can rewrite it in a matrix way like this. And that's a handy way to do things because it generalizes nicely to more complicated systems where we would have more inputs or more outputs. We're not really concerned about ones that have more than two outputs or more than two inputs, though. So the thing that was important to us was the differential gain, which is this number right here, and the common mode gain. That's this number, whoops, right there. And so what we want to do is make the differential gain big and the common mode gain small. So what we can do is we could define a figure of merit, which we'd like to be infinite, but probably won't be. And that would be the ratio of the differential gain to the common mode gain. They call that the common mode rejection ratio, or CMRR for short. It's often written in dB like this right here. Now, we can write the common mode and the differential voltages in terms of the individual voltages on the input, as we've shown before, in a matrix way. You can do it right here, just like this right here. You can do it just like that, with this T matrix being the transformation between the input and the output. Likewise, you can solve this thing backwards by multiplying both sides by T inverse to write the individual voltages, VI plus at the plus terminal and VI minus at the minus terminal, in terms of the difference voltage and the common mode voltage. And this is just the way you do this in a matrix way. So notice we have a new system here, which is 2 inputs and 2 outputs. So instead of having a single output like this over here, we now have to have 2 outputs. So it makes it the output's a 2 by 1 instead of a 1 by 1 matrix. And so we have a 2 by 1 coming in and a 2 by 2 transfer matrix that basically is your gain matrix to give you the output. This is the 2 by 2 transfer matrix right here, just above that. Now, this one is written in terms of the individual input and output voltages on each terminal. And that doesn't matter to me so much. What I really want to look at is the voltage at the difference voltage between them and the common mode voltage. So let's look at how we can use what we had before with our transformation to actually do that. So notice that I would like this thing to be a VI, well, let's see, I'd like a V out differential and V out common mode on there. So what I can do is multiply by the T matrix on the left right here, and if I do it on the left hand side, I have to do it on the right hand side. But I still have this this matrix right here, which is in terms of the individual voltages on the input. So I can use this expression up here and substitute it in for VI plus and VI minus, and now it's in terms of VID and VICM. So I've got V out D, V out CM in terms of VID, VICM. And this new matrix, T, and then this A plus minus matrix that we had before times T inverse, is the matrix that shows me the things I really care about. It has 4 elements. The first one, the 1, 1 element, is a differential differential. That it tells me what is the gain if I have a differential input and a differential output. What's the gain the differential output due to the differential input? And then I have ADCM, and that is the gain that tells me how much the common mode input affected the differential output. Then on the second line, I have how much the common mode gain is affected. And the first term, ACM comma D, is how much the common mode is affected by the differential input, and the second line, ACM CM, is how much the common mode is affected by the common mode. So we would generally want this ADD to be enormous and all the other 3 to be 0. So if I write this, rewrite this equation right here, with that new way of writing the, AD, ACM, and so on, the new matrix, it looks just like this thing right down here. And each of these elements can be found using circuit analysis. And the way you would find ADD, for example, is to find out the output differential voltage divided by the input differential voltage evaluated when the common mode input voltage is 0. Similarly, to find AD, CM, you would find the output differential voltage. You would put in an input common mode voltage, make sure VID is 0, and you'd find the ratio there. And then ACM, D is the common mode output due to a differential input with the common mode input set to 0, and CM is the common mode output caused by the common mode input with the input differential voltage set to 0. Hopefully this was helpful for you to understand common mode and differential amplifiers, 2 in, 1 out, and 2 in, 2 out.